This is 6-4, all about nth roots. All right, so we want to be able to simplify radicals of index n. Some important facts to keep in mind. Even roots always have a plus or minus. This will be important later. Even roots can have imaginary numbers. Odd roots cannot have imaginary numbers, and odd roots do not have a plus or minus in front of them. All right, so think about this, right? If I say, what's the square root of 4, you would tell me 2. All right, if I say, what number squared gives me 4, when we take the square root of both sides, we create the possibility for it to be positive or negative 2. Versus cubed roots, right? So like an odd root, if I say, what's the cubed root of 27? Only 3. Okay, and the same thing, like what number to the third power gives me 27? It's just going to be 3. Okay, there's not a plus or minus there because negative 3 to the third power would give us negative 27. Okay, so just some stuff to keep in mind. Some radical terms. Index, all right, is the number that we are taking the root of. All right, so normally with a square root, we're taking the square root of a number. A lot of times we don't write that too, so if there's no number outside, just assume you're taking the square root, versus if we're taking a cubed root, we write a 3. Fourth root, we will write a 4, and make sure that it's very clear that this number is kind of like closer to the radical. It's kind of like inside this little space between the little check mark and the radical, okay? And this is your radical symbol, and then whatever is underneath your radical symbol is called the radicand. We're not really going to use that very much, but it is something to be aware of. All right, a radical expression is fully simplified when every term's exponent in the radicand, so everything underneath the radical, has an exponent that is less than the index. So an example here, the cubed root of 4 to the 5th, see how this 3 is smaller than the exponent there? That means we're not done simplifying yet, okay? Versus this cubed root of 4 squared, this 3 is bigger, meaning that this would be fully simplified, okay? So you could just say not fully simplified because 5 is greater than 3. Okay, just a little note for yourself. We'll talk about how to simplify them in this section. But right now we're just talking about how we know something is simplified. All right, the radicand has no fractions. So what's underneath the radical needs to not have a fraction. See how this 2/5, it's both the 2 and the 5 are underneath that fourth root. We want to get to a point where we take the fourth root of both the top and the bottom, and then we do some special multiplication to actually get this radical out. All right, so this is not fully simplified, and this is. Okay, there's no radicals in any denominator, so this is no, this is yes. Okay, we want to manipulate it so that square root of 7 would not be in the bottom. And then the greatest common factor of the index and the radicand's exponents is 1. So this 6 and this 3, our index and our exponent here, 6 and 3 have a greatest common factor of 3, so we can actually simplify this further. Okay, so not fully simplified. But then 6 and 5 have a GCF. They have a GCF of 1, so then this one is fully simplified. Okay. All right, the product rule and quotient rule are helpful when simplifying radical expressions. All that means is that if you're multiplying two things together, then they can be put underneath one radical and vice versa. So this will be super helpful. And then same thing with quotients. So if we're taking the nth root of a fraction, we can just take that same index, that root of the numerator and the denominator individually. So let's look at this example. All right, I'm going to show you the way that I like to think about this because it works no matter what. Okay, 72. All right, let's break down 72 into its prime factorization tree. So we want to try to divide it by 2. If 2 doesn't work, we want to try to divide it by 3 or 5. 2, 3, 5. All right, 72 we can divide by, let's divide by 3. We could divide by 2. Doesn't matter. All right, let's divide by 3 though. And then 3 times 24 is what gives us 72. Now let's divide 24 by 2, 3, or 5. We know that 3 times 8 is 24. And then let's break this 8 down into 2 and 4. And then let's break this 4 down into 2 and 2. Now we're going to take groups out. We're going to take numbers out in groups of 3, all right? Because what we've done is we've created 3 times 3 times 2 times 2 times 2. All those numbers multiplied together equals 72, all right? So we're going to take out, look at this, we have 3 2's right here, meaning those are going to come out of the radical as a 1, 2, all right? But this 3 and this 3, they're stuck inside, being multiplied together. Okay, so we're left with 2 times the cubed root of 9. All right, what's really nice about this approach, it works no matter what your index is. Okay, you don't have to memorize perfect cubes or perfect powers of 4. All right, so let's see what happens now. 4th root of 32 over 4th root of 81 using that quotient rule. And now we're going to do the same thing with 32 and 81. And we're going to break them out in groups of 4 because that's our index. All right, 32, let's divide it by 2, 3, or 5. Let's try 2. 2 times 16, and then 2 times 8, and then 2 times 4, and then 2 times 2. We can take them out of the radical in groups of 4. So we have 1, 2, 3, 4 2's. And then we have 1, 2. I'm going to put a box around it because it's left inside. So this is really the 4th root of, well, actually we have that group of 4 2's comes out front as 1, 2. And then we have this 2 stuck inside, okay? And then now 81. Let's take it 3 times 27, 3 times 9, 3 times 3. And then would you look at that? We're taking this out in groups of 4. There are exactly 4 3's here, which means that 81 can be fully simplified as 3. Okay, so our final answer that we're looking for is 2 4th root of 2 all over 3. We are done because 2 and 3 can't be simplified any further, and there are no radicals in our denominator. All right, and so the rest of your notes here are just a bunch of examples. I will go through ones that feel helpful, okay? And then I might tell you to pause the video if it's one that we've already seen an example of, okay? So this one here, square root of 11 over 25, we can break this up like this. All right, square root of 11 is not going to be able to be broken down any further. Root of 25 is 5, and that's it. Okay, put a star by number 4. This one's important. Okay, you see how this is the square root of 7, and this is the 3rd root of 5? Write this down, okay? These don't match. Okay, the indices or the indexes, indices is proper grammar, okay? They don't match. So this is not possible. We could only take the numbers and put them under the same radical if we have the same index there. All right, what happens when we get a bunch of variables here? Step 1, do we have the same index? We have a 5 and a 5. Okay, so we can move forward, and we're going to just multiply everything to be under 1. 9. Why's my pen stopped working? Hello? Oh my goodness. All right, there we go. Now it's catching up. Just fell asleep for a second. Okay, so we're just going to multiply everything to be underneath the same radical, okay? 9y squared x and then 8xy squared. We can multiply our like terms together. 9 times 8 gives us 72. X times x gives us x squared. Y squared times y squared gives us y to the 4th. All right, at this point we should check and see if it can be simplified. So can this 72 be broken down Let's try 236, 218, 2 and 9, 3 and 3. We don't have any groups of 5 of the same number, so the 72 can't be broken down. All right, x squared, this is x times x. That's not a group of 5, so that's stuck. And same thing with the y's. Okay, y times y times y times y, that's not a group of 5. So we are actually all done. Okay. Pause the video and try number 6. Okay, hopefully you recognize that these 6's are the same. So that stays the same. All right, they don't get multiplied together. They just stay as a 6. And then you end up with 8 times 2 is 16, r to the 5th. 16, if we just look at it, it can't be broken down, okay, because we don't have 6 of the same number. We just have 2, 2, 2, 2. We have 4 2's, so it's stuck. And then r to the 5th is r times r times r. Okay, 5 r's, but we can't bring it out as a group of 6. All right, let's see what we can do here. So we're taking the square root of both. A couple ways to think about this numerator. You can think about it as y to the 4th to the 2nd. Square root of 16 is going to be 4. So if we're taking the square root of y to the 4th squared, then we're just going to be left with y to the 4th all over 4. Okay, another way you could think about it is y times y times y times y times, and just keep going. Right? So you have 1, 2, 3, 4, 5, 6, 7, 8 y's, and then you're going to take them out in groups of 2. Okay, and then how many groups of 2 do you have? You have 1, 2, 3, 4 groups, so you're left with y to the 4th. No radical. Okay. Here, let's be careful with our sign out front. It's just going to carry through. All right. And so notice how 3 and 2, that x squared, that's a smaller exponent than the 3, so we actually can't do anything with that x. Y to the 12th, though, 12 is bigger than 3. So what we can do, we can do 12 divided by 3, and that's going to give us y to the 4th. That's one shortcut as well. Okay. Another way to think about it, cubed root of y to the 4th to the 3rd, right? And then those would cancel, and we're just left with y to the 4th. Okay. All right, a few more examples. Let me see if there are any that we need to go through. So this is the case where we can look at this 12 and this 3 and say, okay, you know what? They can be divided by each other. 12 divided by 3 is 4. So we can just change the index. Okay, so this is equivalent to the 4th root of 2. And then same thing here, 6 divided by 2 would just become the 3rd root of t. Feels kind of funny. The more practice that you do with these, the more you'll see, oh, there are patterns and all sorts of things that make sense. All right, 25p to the 7th. A couple ways to think about it. You could say, oh, I know the square root of 25 is 5, and then how do I deal with this p to the 7th? 5 and then p to the 6th times p, and then that p to the 6th can be rewritten as p to the 3rd squared, and then it's going to come out front as a p to the 3rd, and then the square root of p is left inside. Number 12. This one's a fun one because we can actually break down our 72. Okay, 2, 36, 2, 18. So remember, we're just dividing by 2's, 3's, and 5's every time. All right, 2, 9, 3, and 3. And our index here is 2, taking the square root. So we're going to bring numbers out in groups of 2. So we have 2 2's, 2 3's. This 2 is left by itself. So the ones that I circled are going to come out front once. And then this 2 that I put a box around is stuck inside. with our y to the third x. All right, so we end up with 6 square root of 2 y to the third x. And then this y to the third can be thought of as y squared times y, meaning that this y squared, the square root of that is going to be y, so it will come out front. Okay, but then the other y is left hand side along with that x. Oh, and I lost my 2 somewhere in here. That 2 should be there. Okay. All right, just a couple more. If you're recognizing that this just takes practice, then you can stop here if you would like. If you want to finish this out, and let's go for it. Okay, cubed root of negative 27 is negative 3. All right, so sometimes when I'm working through these, I just write my radical and then I leave space and I bring out what I can. Okay, so now I'm done with that negative 27. I know this y to the 7th can be y to the 6th, and there's going to be a y left. That y to the 6th is going to come out front as a y squared. Okay, x to the 5th, it can be thought of as x to the 3rd times x squared. And so this x to the 3rd is going to come out front as just an x, and then we're left with an x squared inside. And then the z to the 6th will be out front as a z squared, because it's like z to the 3rd times z to the 3rd, right? There's two groups of 3 z's being multiplied together, and so that's what we're left with. All right. Last one, almost done. Think about this: 32, 2, 16, 2, 8, 2, 4, 2, and 2. We want to break out those 2's in groups of 4. Okay. All right. So this group of 4 is going to come out front. That negative is going to follow us through. There's a 2 stuck inside, so we're done with our 32. A to the 5th, 5 minus 4 is 1. A to the 4th times a, so we're going to have a and a here, right? A to the 4th, a to the 1st. And then this 4th root of a to the 4th would just be a. That's how we got this. And then a to the 1st is stuck inside. All right, b to the 7th can be thought of as b to the 4th, b to the 3rd. So we'll have b to the 3rd here stuck inside. And then this b to the 4th, when we take the 4th root of it, is going to come out front as a b. That's all. Try your practice. See you later.